All right. Happy Thursday. I'm so happy that I get to be back teaching again. It's been way too long. Last week was rough not being able to be here. Sorry that you had to watch the pre-recorded videos, but here we are. Get some new material. We get into chapter 8. So today in chapter 8, we're going to talk about the distribution of sample mean for the normal population, and then touch on what to do if we have a non-normal population. And that's like 2 slides. And then section 8.2, we're going to talk about the sampling distribution of a sample proportion. And then we're going to talk, actually compute the probabilities with a sample proportion. So this, even though it is like 2 days of lessons put into one, since we just had office hours on Tuesday, it shouldn't take too long because they're small sections. So it really shouldn't be too long. But I don't know, I had something in it left. It's been a really long week. All right, let's just jump in. Guess I need my iPad for that. All right, so a sampling distribution. So what a sampling distribution is so if I took, it is a statistic, so it's based on samples. So if I took a sample size n, so that means just you chose your sample size, and then you took every single sample of that size that you possibly could take out of a population, that would be a sampling distribution. So don't worry, you're not going to have to define these terms. So a sampling distribution of a sample mean is if I took every single sample that I could of whatever size sample I decided, and I took the mean of every single one of those samples. So I took every single sample and I took the mean of every single sample. Then what I do is I take all of those sample means and I find the mean of all of those means and the standard deviation of all of those means. So what happens is it gives us a really good estimate of our population. And I know this is kind of confusing. Hopefully, once we start doing examples and mathing it out, it will make more sense. But don't worry, you don't have to define this. I'm not going to ask you to define what a sampling distribution is of a sample mean. So, but basically, we're just finding a bunch of different samples, find the means of all those samples, and then find the mean of all of those means. That's essentially what it is. Here's a kind of an idea of what it is. So we take, the government wants to figure out the average income of all US households, and you can't survey every household in the US. That would be basically impossible. So what they do is they take a sample of 250,000 people, they randomly select them, and they find the average of those, of the average income of those 250,000 households. Then they take another sample, and this is going to be a different sample. So it's not going to be all 250 of the same people. It could have some of the same people, but it's not going to be all 250,000 of the same people. So take another random sample of 250,000 households, and you find the average of all of those. Then we do it again, the same thing. So because every one of our samples is different, the means are all going to be different. So that means our sample mean is going to be a random variable because all of those means are going to be different. So the way that we find a sample distribution is you find a sample size n, whatever your sample size is you choose. Chapter 10 is when we're going to figure out how to find a sample size or how to know what size of a sample size to use. So we're going to talk about that in chapter 10. So just ignore that for now. So you choose your sample size and you take a random sample. Then you find the mean of that sample. Then you do it again. Take another sample and then you find the mean of that sample. And you keep doing this until you get every possible sample. And once we take one sample one time, we can't take that sample again. It makes it really easy if it's like a small amount of people. So like, for example, let's say that these were the 3, let's pretend this A, B, and C are my population. and I'm going to get all of the samples of size 2 that I can out of my population. So one sample would be AB, the other sample would be BC, and the other sample will be AC. That is every possible sample of size 2 of that population. Now you just apply it to something a lot larger than that, and you kind of get an idea of what we're talking about. All right, so here's an example, and we're gonna kind of give you some diagrams so you can get an idea of what it looks like with different sample sizes as we go. Oh, hello, Guy, welcome. See you popped in here. All right, so the weight of pennies minted after 1982 are approximately normally distributed. The mean is 2.46 grams and the standard deviation is 0.02 grams. So we want to approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n equals 5. So we're approximating the sampling distribution because I can't take every sample of size 5 that exists of pennies minted after 1982. It would be impossible because I can't find all the pennies minted after 1982. So we're approximating the sampling distribution. So my samples are going to be on the other side on the next slide. But so I took 200 simple random samples of size n equals 5. So this is the 5 pennies that I chose. And I weighed each of those 5 pennies. This is just one sample. And then I found the mean of that sample. So this is the mean of just this sample. So I did this 200 times. 200 times, I randomly selected 5 pennies and found the average of their weight. I did that 200 times. Here it is. This is the average weight of 200 different samples of size 5. Don't worry, I'm not going to ask you to do anything with this. I'm not going to ask you to put it into your calculator or Excel or anything. You're just looking at it and saying, man, that's pretty. So there you go. So I took the average of all of these averages. Since each one of these is an average, I took the average, or I took the mean of each of these averages. So I got this right here. The standard deviation of all of those averages, of all of those means, was 0.0086. It is much smaller than the standard deviation of the population. So if I'm averaging all of the averages, we would expect that to be really close to the middle. You're expecting that to be closer to the real average. Therefore, your standard deviation should be small. So let's take a look at the histogram on the next page. So here's the histogram of all of the sample means of size of my samples n equals 5. So they're pretty close together. It looks all spread out, but take a look at the numbers down at the bottom. This number right here, say it's about 2.40. And then up here, we're at about 2.48. So they're very close together because remember, these are the averages. It makes sense they'd be close together. Still a pretty nice bell curve. Yeah, that goes up above there a little bit, but it's definitely not skewed. And if it is, it's not by much. So it's pretty normal. And since the population is normal, we would expect the averages of all of the samples to be normal. So let's take a look at what role the sample size plays in our standard deviation of the distribution. So we're going to play around with our sample size a little bit. So this is really important. I'm thinking there might be a question. I think it's on the homework. It might be on a quiz, but I think it's on the homework. As the size of the sample increases, the standard deviation of the distribution of sample means decreases. As we get larger sample sizes, our standard deviation is going to get smaller. And this makes sense because we're taking a larger portion of the population. So we're going to be closer to what the actual population mean is. So as your sample size gets bigger, the standard deviation of your distribution is going to get smaller. Give you a second to write that down because it's important. So let's take a look. We're gonna get some bigger samples and we're gonna see what happens. So we're gonna approximate the sampling distribution of the sample mean. We're gonna take 200 simple random samples of size n equals 20. The mean of our population is 2.46 and our standard deviation is 0.02 grams. Let's take a look. So this is with sample sizes 20. So we're getting even closer to the middle. So when we had size n equals 5, it was 0.0086. Take a look at how much smaller it is now. It's about half that. My standard deviation is now about half that. So there's less variability there. It's getting closer to the middle because I took those larger sample sizes. All right. So when we are looking at the mean, so we're going to look at the mean and the standard deviation of sampling distributions. So our standard deviation of these sampling distributions depends on the size of our sample. As we saw back here, my standard deviation gets smaller with larger sample sizes. So the sample size matters when you calculating the standard deviation. Let's take a look. So important, the mean that we are going to use is just going to be the mean, the population mean that we have. If you're given a population mean, that is the mean we are using for our sampling distribution. The standard deviation, we use this formula right here. So you take this population standard deviation and divide it by the square root of the sample size. So take the population standard deviation and divide it by the square root of the sample size. You will see it called standard error. Standard error is one of the terms that we use. So this right here is standard error. They will call it standard error and they will call it standard deviation. You will see it both ways. When I'm trying to give you homework help, if you email me or message me through My Open Math or through Blackboard, I'm going to call this the new standard deviation. Just to differentiate it.
Symbol.
Yeah. But just to differentiate it from the old one, our regular standard deviation, I'm going to call it the new standard deviation. Hopefully that makes sense. Questions before I move on? Did you say something, Guy? You've like sounding really quiet tonight for some reason.
Can you hear me?
I can hear you. There you are.
Oh, maybe my microphone. Other earbuds. That's funny. Yeah, I have
Oh,
earbuds. I'm like at the campus because I have a computer lab aide position, so I'm technically kind of like at work.
you're working. You're getting paid
I'm
to go to
working.
school.
Yeah, no, earlier I was just saying, so the square root of
Yes.
n is what you're calling standard error or standard deviation.
Now the sigma divided by square root of n is our sigma or standard deviation. So
Oh, I see.
this whole thing,
N
n
is the
sample
number.
size. N is the sample size.
N is sample size. Thank you.
Yes. You're welcome. That's what the arrows are pointing at. Sorry, it looks like it's n.
It is kind of looking like it's
Okay, here. There we go. More arrows. Does that help?
Yeah, just keep going with the arrows.
I could do this all day. Just kidding.
Okay, yeah, one more.
One more. Okay. There we go. Now it's clear, right?
Yeah.
Okay, perfect. We'll move on. Okay, so let's so take a look at our calculation. So with our standard, the standard deviation of the population is 0.02. This is the pennies. And we use the sample size of square root of 5. So with our calculations, we get 0.0089. This is very close to the 0.0086 that we found by actually mathing it all out. I don't think anybody is going to be mad about us being 3/10,000ths off. It's not going to be noticeable. 3/10,000ths of an ounce is not going to be a noticeable difference. So by mathing it out this way, it makes us not have to put them all into our calculator and run the one variable statistics. Nobody wants to do that. And I'm not going to make you do that because that was 200. That would take a long time. I don't even know if the calculator can handle it. I've never tried. All right, moving on. So now let's say, look at the sample size of 20. So I did the same math, but I used the sample size of 20 and I get 0.045. This is exactly the same as the approximate standard error we found earlier. It's exactly the same thing as when I found all of those manually. So that's good. My math checks out. I like when that happens. So this is how you calculate standard error or new standard deviation, or if they ask for standard deviation of a sampling distribution. So this only applies when we're working with mean and standard deviation. Questions before I move on? All right. So if our random variable X is normally distributed, the sample mean will be normally distributed. This is important information. If your random variable X is normally distributed, the distribution of the sample mean will be normally distributed. Normal equals normal. Oops. Important stuff. Boom, 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 boom. There we go. I'm pretty sure something like this shows up on a quiz. Asks like when it's normal or something like that. Pretty darn sure. All right. So the intelligent quotient, or IQ, is measurement of intelligence from a standardized test. So our scores are approximately normally distributed, and our the mean score is 100. So the average IQ is about 100. Standard deviation is 15. So if we took a bunch of sample sizes of 9, we want to know what the mean of the sampling distribution is and the standard deviation of the sampling distribution would be, or you can call it standard error. So this is either standard deviation or it's standard error. These are the two ways you are going to see it on your homework. So let's math it out. Okay, so my mean, mu sub x bar, is just what they gave us, 100. The mean is always just whatever they gave us as the mean. It doesn't change. The standard deviation sub x bar is going to be the standard deviation they gave us, which is 15, divided by the square root of 9. I love it when it's math that I can do in my head. 15 divided by 3, so that is 5. So if we were working with, if we're doing any math with this, so if I was going to be doing anything with normal CDF, this is the standard deviation I'm going to use. So if I'm working, if it is going to ask me the probability of something happening and they give you a sample, use that. If you're dealing with the population, use the population standard deviation. We should be getting some examples in a minute. But if they're talking about samples, use this. If they're talking about population, use that. You will see. We will do examples. And all of my red arrows everywhere. Okay. See, this is the example I was just telling about. The weight of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation 0.02 grams. We already know that. What is the probability that a simple random sample of 10 pennies minted after 1982 will have a sample mean of at least 2.465 grams? So we're looking for the probability that the sample mean is greater than or equal to 2.465. That's what we're looking for. The probability that we take one, actually it shouldn't be that, but hold on, don't write that. Write this instead. So we took one random sample of 10 pennies. We want to know the probability that its mean is at least 2.465 grams. So we're going to use normal CDF. And we're doing 2.465. And our upper is 1E99. I really got to putting a lowercase e. My high school kids keep getting mad at me for that, and I need to listen to them. And then our mean is the 2.46. I need to calculate the new standard deviation. So I'm going to take for my, So I have my sigma sub x bar equals 0.02 is the population standard deviation, and we're looking at 10 pennies. I'm going to map this out with my fancy schmancy calculator. I got approximately 0.0063. So this is the number that I have to put in here. I'm using the new standard deviation because I'm dealing with this simple random sample, and I want to know the probability that we have a sample mean. So it's asking for the probability that a sample mean is a certain amount. All right, I'm going to put that in my calculator, my normal CDF here. Second vars, normal CDF, 2.465, 1E99. 2.46 is my mean. 0.0063 is my standard deviation. I have approximate 0.2137. So the probability that a simple random sample of 10 pennies minted after 1982 has a sample mean of at least 2.465 grams is 0.2137. Questions? Okay, I want to show you all something cool with the calculator because I know that you all like cool calculator things as much as I do. Maybe not as much as I do, but pretty darn close. So let me get to my calculator up here. Okay, I'm going to do this problem again, exact same one we did. So I did second vars and I'm going to normal CDF. So my lower is 2.465. My upper is going to be infinity or 1E99. My mean is 2.46. Okay, this is where the fancy comes in. You can do math in these boxes. I don't have to calculate that standard deviation outside of this box. I could put 0.002 divided by square root of 10 right inside this box, and it will just math it right there. So you don't have to do it separate. You can just put it in here and let it math it right there. I do this all the time. And then enter, and it's what I did something weird. Something I did wrong, because that shouldn't be that number. See, I'm getting all excited and I did something wrong. I don't know what
Maybe you should have put the 0 or 0.02 in parentheses.
Oh, no, you know why? It's because I put an extra 0.
Oh, that's it. Yep.
That makes a difference, doesn't it? Okay, I fixed it. See, I fixed it. Let's try it again. Look at that. That's the right answer now. No, it was just because I had an extra 0 in there. I got so excited about the math, I threw an extra 0 in. So this is the exact same answer I got before. Actually, this one is more accurate than I got before, because was no rounding involved. And that's why I like this. That's why I like to put the math in the boxes, because I'm doing no rounding elsewhere. And I can just round it at the end. And this number is still basically the same thing. It's slightly better. This one is 0.215. And
Would
mine,
you mind going back that one step just so I can see what you entered for the standard deviation, like how exactly you entered it on the calculator, please?
so I'll clear it out and I'll do it again. So I have 0.02 divided by the square root of 10, because 10 is my sample size. So you can just put the math directly in there. Whatever formula or calculation you would be doing on your calculator, you can just put it directly there. And then hit enter. Hit enter again. And I've got my numbers.
Got it, thanks.
You're welcome. It's really cool. I just love fun calculator things. And that works for any boxes. So any of those things that you're doing math in, it works. And I mean, that right now, that's kind of all we have, but there will be other things later on where you're going to want to do the math in the boxes. So any of those things, the normal CDFs, or we're going to be doing some prop Z intervals and all sorts of fun stuff later. And all of them, you can just do the math directly in the boxes. It's kind of cool. It is kind of cool. All right. So because we like diagrams, and unfortunately I lost some of my formulas. For some reason, the textbook likes to turn everything into Z-scores. And I don't know exactly why, but they like to turn everything into Z-scores. And so here's the same math that we just did. And but they turn it all into Z-scores, and they got basically the same answer, slightly different, but they get basically the same answer. Because I think the other was 2.2146. But I don't know why they put everything into Z-scores, but they like to do that. I think it's extra work personally, but this is your normal CDF stuff right here. And it's just showing that we're looking at this portion. This is the area of the curve that we're looking at. That's all that this is showing. I love the diagrams though. The diagrams are super helpful. Get out of there. Okay. All right. So here's another example. So the IQ of humans is approximately normally distributed with a mean of 100 and a standard deviation of 15. Didn't we just do this? No. Okay. I want you to try this. I'm going to work quietly behind you, but I'm going to let you get a head start. So find okay, so your standard deviation is the same, but find the probability that a random sample of size 10 has a mean greater than 110. Oh, no, this isn't the same example. Sorry, it's not the same standard deviation. For some reason, I thought this was pennies again. So we're looking at IQ, mean of 100, standard deviation of 15. So you're going to want to find the mean and the standard deviation, and then do normal CDF to calculate the probability that you'll get a sample with a mean greater than 110. That's what we're doing. So just like I did on the other one, but with new numbers. that. Oh, apparently I can't. I can math, I just can't write the math down.
Um,
Yeah.
sorry if I missed this spot. You know that square root that has the 10
Yes,
under the 15?
yes.
Are you just supposed to square root that mean? And
No,
is that how you got that 10 or?
no, you're square rooting the
Oh
sample.
no, I see the N. I see the N over there. Okay, I hadn't seen things.
Anyone else? Any other questions? Did we all get the? We all get the same answer? Or in rounding different, it could be slightly different, but how'd we do?
If you do it the extra math way, where
Uh-huh.
it's 0.0175.
Okay, let me do it that way also. Divided by, so you put the math in the calculator, okay, I got, yeah, 0.0175, yes. Yep, I got the same thing. And also, I think maybe my last one, no, it was, yeah, you're good. You are good. So, this would this be unusual? Would it be unusual to get a sample of size 10 with a mean of 110 or greater? Would that be considered unusual? Since-
Hmm,
Okay, go ahead.
I think it's no.
Okay, so what is the percent cutoff for unusual?
Is it
2.
5?
It's 5. Anything less than 5% chance of happening is unusual. So this is 1.74%. So this would be unusual. It would be unusual to find a sample of size 10 of people who have an IQ of over 110. Now this is of all humans. So you're not like grabbing kids out of AP classes or anything that. This is all humans. Even though I don't know if their IQs are better or if they just work harder, I don't know. That would be an interesting study. Any questions on this other than my rambling? All right, I'm going to move forward. So sometimes we have a population that is not normal. So for example, rolling a die, it's going to be a uniform distribution. It's not normal because it's uniform. And so that the population distribution is not normal. This happens quite frequently. We have an average of 3.5. Our standard deviation is 1.708, and it is just not normal. What we do in that case is I'm going to show you what happens. So I'm going to first start with a simple random sample of size 4, and I'm going to take 200 random samples of size 4. Then I'm going to take 200 random samples of 10, then 200 random samples of 30. And I'm going to show you the histograms and what happens as our sample sizes get bigger. So this is with 4. I mean, it's more normal than the other one. It's actually, looks like it might be slightly skewed right, but it is definitely more normal. Take a look at 10. This is pretty normal. Take a look at 30. This is like a perfect, this is like a perfect graph, a perfect normal distribution. So as you notice, as the sample size got larger, the sampling distribution became more normal. I'm going to give you the words for it on the next page. So here it is right here. This is right here, the central limit theorem. I'm not going to require you to remember the name, though it's not a bad idea, but I'm not going to require you to remember the name, but what it says is what is really important. The shape of a distribution of the sample mean becomes approximately normal as the sample size increases regardless of the shape of the population. So as our sample size, if our population is not normal, as our sample size gets larger, the shape of the distribution will become normal. I'm going to give you a moment to write that down. Because I'm thinking you might have to answer it on a quiz.
Wait, what? Sorry.
You might have to answer on a quiz. It might ask you when the sampling distribution of sample means is normal. And it's normal if our population is normal or when the sample size gets larger. Because as the sample sizes get bigger, the shape of the distribution becomes normal or approximately normal. We don't deal in absolutes. We say approximately because we're crazy like that. All righty, I'm going to move forward. Okay. So suppose the mean time for an oil change at 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2. So we're going to talk about the sampling distribution of our sample mean if we have a random sample of 35. All it means when it says to describe the sampling distribution, all it means is to give the mean and the standard deviation. That's all it's saying. It's not looking for anything fancy. It just wants you to give the mean and the standard deviation. So I'm going to give the mean is just what it gives us. It's 11.4. So our average time for an oil change is 11.4. The standard deviation is 3.2 divided by the square root of 35. So let's math that out. This gives us approximately 0.54. So that's all we're doing when we're describing it. We're telling the mean and the standard error or new standard deviation. So now it's asking us if a random sample of n equals 35 oil changes is selected, what is the probability the mean oil change time is less than 11 minutes? So we're looking for the probability that our X bar is less than 11. So use your normal CDF down there. My lower bound will be negative infinity. My upper bound is 11. I got approximately 0.23. How'd we do? I'm going to do it the other way with the math in there also and see how different it is. Still 0.23. All right. How'd we do? We're there? We're good? Questions? I think this is the end of this section. Yes. Okay. So if you keep track of that sort of thing, we are now done with 8.1. We're going to jump into 8.2. Okay. So we are renaming something we've already used like 20,000 times because this is what we do. So we are now dealing with population proportions. Set aside your we're still going to look at mean and standard deviation. We're going to get there in a different way. So when we're given something like a a certain proportion of the population has some characteristic. We're dealing with with proportions and not means and standard deviation. When we are estimating a sample proportion from a population, we have a sample proportion, we call it p hat. Anytime something is an estimate, you throw a hat on it. I don't know why, but it is what we do. So in an observation, this would be the number of successes. And then this would be your sample size. This should be very familiar. This was how we calculated relative frequency. This is how we calculated experimental probability. It is the same thing. It is the same thing. So this is your p hat. This is your statistic that estimates the population, estimates the parameter. So p hat is a statistic. P is a parameter. There we go. I don't want to write with black anymore, so I'm getting rid of that. Okay, let's move on. So Quinnipiac University poll. Now, so I didn't even know how to pronounce Quinnipiac for a long time. And then I had a student who knew something about Quinnipiac, and that's how they told me to pronounce it. So I believe them. I don't know if it's true or not. Anyway, 1,745 registered voters nationwide in 2008 were asked whether or not they approved of the way George W. Bush was handling the economy. 349 responded yes. So our point estimate, our p hat, is the number of successes, the number of people that said yes, over how many people were polled. And of course, it's one that it's already on there. So about 0.2 or 20% of the people at the time approved of the way that George W. Bush was handling the economy. That's all there is to it on finding the p hat. So it's just the number of successes over your sample size. I think I might have one more. I do. Let's do one more. Opinion Dynamics Corporation conducted a survey of 1,000 adult Americans 18 and over. They asked if they were on some sort of a low carbohydrate diet. Of those surveyed, 150 said that they were on a low carb diet. We want the point estimate for the proportion of Americans who are on a low carb diet. Once again, p hat equals. So we have 150 successes over 1,000 adults. And I bet I could do this in my head, but I don't trust myself. So yeah, I could have done that in my head. So 15% of that sample stated that they were on a low carb diet. Any question about p hat? All right. Okay. So we're going to talk about we're going to do some histograms on the following page. This is similar to what we did with our mean. So according to a time poll conducted in June 2008, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. So we're going to look at the sampling distribution for the sample proportions for sizes N, 10, 50, and 100. So basically what we did is we take a bunch of samples of size 10, and we find the proportion of people that are successes or that believe that gay and lesbian couples should be allowed to marry in each of these. So we took 10 and found that proportion, and we did it again and again and again. Took a lot of different samples. And then we did same thing with 50. Our sample size is 50. Take a bunch of sample sizes of 50. So that's what we're doing. So here's the first one. So when I took sample sizes of 10, I took 300 different samples of size 10. You can see that we're kind of skewed right, but it's almost normal. And we have a mean of 0.426, which is somewhat close to our population. We have a standard deviation of about 16%. We're going to move on. Here's my sample size 50. Look at that. Look at the difference. So we had a 0.16 standard deviation here. Sample size 50. Our standard deviation is only 0.072, and our mean is 0.426 still. Okay, let's look at our bigger sample sizes. Look at that. Sample size of 100. We are now at the same mean as our population, and our standard deviation is 0.047. So it is getting smaller and smaller. Once again, larger sample sizes make you have more normally distributed. It's the same thing with sample proportions as it is with sample means. It's going to say that right here. So this is their key points. As the sample size increases, the shape becomes approximately normal. As the sample size gets larger, the sample proportion is going to equal the population proportion or get really close to it. Also, as our sample size increases, our standard deviation is going to decrease. All things that you expect to happen. So sample size gets big, we get approximately normal, our mean gets close to the population, and our standard deviation gets really small. I'll give you a minute to write all this down. We really don't have a ton left. I know we're already at 6:30. I've spoiled you guys by usually getting done pretty early, but we really don't have a ton more. This section isn't super long. All right, moving forward. So just like with our means, we need to have a new standard deviation. But before we get there, we're going to talk about a couple of things that we need to happen. So remember I said that as the sample size gets bigger, our population becomes approximately normal. We have a little formula to basically test if our population is large enough. This is it right here. So when you are taking your quiz, which is coming up which is at some point this week or before Tuesday, if it asks you when your sampling distribution of the population proportion or sampling distribution of p hat, when it's normal, this is what you're going to say. As the sample size gets larger, as long as NP times 1 minus P is greater than or equal to 10, our sampling distribution will be approximately normal. This is what you're going to say. For the mean, we just use whatever we're given for P. Whatever they gave us as a population proportion, that's our mean. Then finally, this is the lovely formula that we use to find the new standard deviation. So for proportions, this is your new standard deviation. This is what we use because once again, the standard deviation is dependent upon sample size. So we have to use this fancy schmancy math. And you're using P and not P hat. In here, use P, not P hat. Questions before I move on? I'm going to do some examples. Okay. So another thing that we need to take into consideration, which it might ask you, but all of the examples we use are going to fit this condition, but just kind of be aware that it must be. So even though our sample size has to be big enough to do the NP times 1 minus P, our sample size can't be larger than 5% of our population. Because if our sample size gets too large, when you're taking lots of samples, you're going to be sampling a lot of the same people or same things. So your sample size cannot be more than 5% of the population. That makes sure that the sample values are independent. We can only guarantee that they are independent, that the samples are independent, if it's less than 5% of the population. I'm not going to give you any that are not less than 5% of the population, but keep this in your noggin that it has to be a thing. Okay. But even if this isn't true, which it's going to be true in every example we do, even if this isn't true, you're still going to use this new standard deviation. We just can't guarantee that we have a normal population. But I'm not going to give you anywhere that's not true, so it's not a big deal, but just letting you know it's a thing. Okay. We have 7 slides left. We've got this. So according to the Time poll conducted in June 2008, 42% registered voters believe gay and lesbian couples should be allowed to marry. We have a random sample of 50 voters. We have this happening up here. We want to describe the sampling distribution of the sampling proportion. What it means to describe it is just to give the mean and the standard deviation. So here we go. Our mean sub p hat just equals the population proportion that they gave us. That is our mean. Our standard deviation sub p hat is going to be the mean that they gave us, or the proportion they gave us, times 1 minus the proportion that they gave us. I don't know why I put a 0 in that one, not the other, divided by our sample size. So again, I'm going to put this in the calculator and calculate this out. You can, if you are careful with your parentheses, you can put this whole thing in your calculator. If you don't trust yourself, then do it a piece at a time. But if you're very careful with your parentheses, you can put it all into your calculator at once. That doesn't seem right. See? I see what I did. Okay. See, I wasn't careful. And I ended up with weird numbers. I ended up with a standard deviation of like 0.7 or something. So that still seems high. Oh, it is high. Y'all shouldn't trust me with a calculator, seriously. Let's see here.
90697997135.
Yes. And basically that right there. Yeah, I put 5 instead of 50, and you get a really big answer if you put 5 instead of 50. Is that what you got, Guy?
Mhm.
0.0698?
Yep.
I got the same, but I did piece by piece.
Perfect. Okay. Yeah, the first number I ended up with was 0.69 because I didn't put a decimal in my 0.58. And then, I did some really wacky stuff. So sometimes we just don't trust me. All right. This is all you're doing to describe your sampling distribution. You just give me the mean and the standard deviation. If it asks to describe it, that's all you do. Okay, let's move on. So we can guarantee, the n equals 50. So our sample size is definitely smaller than the population size of all registered voters. So that's good. These are the things we have to check. So also NP times 1 minus P, I calculated it there. It's 12.18. We're good. It's greater than 10. So now we can state that it is approximately normal. Our mean is 0.42 standard deviation. They mathed it out. They got the same thing as us, so we must be good. This is very close to the 0.72 that was in our simulation back a ways. Let me see here. Find it. This one right here, we got 0.072. Very, very close. So we did some good math there. All right. Any questions before we do another example? So we're going to do another one. I would like you to calculate this one. I'm going to be behind you. So based on a study by Gallup, 76% of Americans believes that the state of moral values in the US is getting worse. I bet you it's worse now. This was a long time ago. Suppose we obtain a simple random sample of 60 Americans and determine which believe that the state of moral values in the US is getting worse. Describe your sampling distribution. So what you're doing is finding the mean and the standard deviation. I'm just going to put the symbols down. I'm going to work behind you quietly after you get started. All right, how'd we do?
I got 0.055.
Yep, that's what I got. Looks like we did good. So our mean, we keep the mean is 0.76. It's the same as the population proportion. And then our standard deviation, 0.055. Good job. Okay, any questions? We have 4 slides left. We're almost there.
Why are we subtracting it from the 1?
Because this is the probability of success and this is the probability of failure.
I see, thanks.
No problem.
You
That was-
can kind of look at it. So it's being 0.24.
And I used to write 0.76 times 0.24, but every single time I had somebody say, where did the 0.24 come from? So I quit doing that. But you are more than welcome to just do that. But every single time I have somebody ask me where the 0.24 came from, so I quit doing that. And every single class I've taught, this is actually only the second term where I haven't done that. I haven't just done 0.76 times 0.24. I was like, you know what? I'm just going to do the 1 minus, and you guys can math that out if you'd like. All right, moving on. Okay, so now we're going to actually math this out. So according to the centers, we're going to actually do some probabilities. According to the Centers for Disease Control and Prevention, 18.8% of school-age children ages 6 to 11 were overweight in 2004. In a random sample of 90 school-age children, age 6 to 11, what is the probability at least 19% are overweight? So we're looking for the probability that probability that p hat is greater than 0.19. My pen just randomly changes colors. I'm going to do this calculate the new standard deviation down below because I don't have enough room. So my mean sub p hat is 0.188. So my standard deviation sub p hat is going to be the square root of 0.188 times 1 minus 0.188 divided by 90. This is going to be standard deviation here. Parentheses are your friend, just in case you wondered. Divided by 90. I got approximately 0.041. That's my standard deviation. The nice thing, one of the nice things about this is most of the time when we're dealing with proportions, we can't use normal CDF, but since we've converted it to sampling distributions, now that we have a mean and standard deviation, we can actually use normal CDF. So I'm going to use normal CDF. And I want at least 19%. So I'm going to do 0.19 to 1E99. And then 0.188. And our standard deviation is that number that I just calculated right there. So use your normal CDF and see what you get. I got approximately 0.48. How'd we do?
Yes.
Yes, okay. All right. So this next question, there's a couple of different ways that we can answer it. And so let me talk about it first, and we will talk about the different ways we can do it. So we take a random sample of 90 school-age children. The results in 24 overweight children. It says, what might you conclude? So this is going to require you to use your imagination a little bit. So probably the way that I would do this is I would just use my normal CDF. So I need to calculate the p-hat. So remember, your p-hat would be 24. This is how many overweight children we had over 90. So this is going to give me a p-hat of about 0.267. So one of the ways that I can draw some conclusion here is to find the probability of finding greater than or equal to, so finding a probability greater than or equal to 0.267. This is probably how I would do it. I would do my normal CDF. So I get 0.267, 1E99, 0.188, then 0.041. This is my favorite way, my preferred way to do it, but I'm going to talk about the other ways in just a second, because some people have different preferences than I do. So when I use my normal CDF, I get this probability, unless I put it in wrong. I got a probability of about 2.7% chance. There's a 2.7% chance of finding 24 overweight children out of 90 in a random sample. So the conclusion, when it says, what might you conclude? This is where you kind of use your imagination a little bit. So one thing that you might conclude is that the actual population proportion is probably wrong. Maybe it has changed. That's one conclusion that I might draw. You might conclude that you just happen to have, you happen to choose a sample that was unusual, and you might just want to draw another sample to see what, you might want to try another sample just to see if you get another outlier for an answer. So you're just kind of drawing your own conclusions here. What might you conclude? Because this is clearly unusual. It would be unusual to get this sample. Another way that you could have done this is you could have calculated the z-score of this right here. So I could have done, I'm not going to calculate that z-score, but I'm going to show you how I would. 267 minus 0.0188 divided by 0.041. And you're going to get a number greater than 2, which would show you that it's an outlier. Another thing that you could have done is you could have added 2 standard deviations to your mean and found that upper bound to notice that this is outside of that. So all of the things we have done before, you can still do here. I prefer the normal CDF. Any questions on that? I know that was a lot of words. All right. Let us move forward. Oh, look, they already mathed it for me and I didn't even need to do all that math. Uh-oh, what happened? Oh, I hate when this happens. Okay. There we go. I don't know what happened. Okay. So, 90 was less than 5% of our population size. We're assuming that it's all children between 6 and 11. And our NP times 1 minus P, it was greater than or equal to 10. We're good. So we're approximately normal. Our mean was 0.188. Here's all of our math. Those are the numbers we got, basically. Yes. Okay, they just went one more out than we did. So in a random sample of 90 school-age children, see, they did the Z-score. Look at that. Oh, this is the other one. That's the same probability that we got. So there's a 48% probability we'd get a sample with at least 19% overweight. So this was all good. This is the same math we did. They just did it fancy, and I didn't remember it was there. So, and this is our math that we did on the other one. So what it says is we would only expect to see about 3 samples in 100, resulting in a sample proportion of 0.2667 or more. It's unusual if the true population is 0.188. They didn't even draw fun conclusions, which I like to draw fun conclusions. They didn't even do that. Rude. So this is just the same math we already did. They just put fancy words on it. Okay, we have one more slide. I think it's another example. Any questions before we move on? All righty then. Here is our next example. According to the National Center for Health Statistics, 15% of Americans have hearing trouble. In a random sample of 120 Americans, what is the probability at most 12% have hearing troubles? I'm going to write this probability of what we're looking at here. Oh, if I can, I'm having issues. P hat, so it would be less than or equal to 12.12, sorry. That's what you're looking for. What I would like you to do, I would like you to calculate the new standard deviation. Then I would like you to calculate that probability using normal CDF. If you're ambitious, feel free to move on to B, but I'm going to jump to that in a minute. I will work quietly behind you, but let you get a head start. So go ahead and get that started. That went too far out. We'll fix that. do this. Do y'all get approximately 18% probability? All right. So now it asks,
No,
you didn't get that? What'd you get?
I got a 0 for some reason. I don't know.
So go back and check your inputs for your normal CDF. So I put -1E99 for my lower because we're doing less than, and 0.0 or 0.12 for the upper, 0.15 for the mean, and 0.033 for the standard deviation. It's possible you typoed because I do that all the time.
That's what I did.
It was a typo?
Yeah.
Yeah, it happens. I was doing them left and right earlier. So once you fix that, hopefully you'll get about 18%. Did you get 18%, Guy?
I did.
Okay, cool.
Maybe just enter the numbers into the web browser calculator for everybody to see.
You want me to do that?
Yes, please.
Okay. All right, if I can find it. I think so my web browser.
Okay. It's actually just me and Nancy. Never mind.
No, it's fine. I can do it. It should only take a moment to get that back up. When my computer went weird. Yeah, see, there's a problem. It's not opening another window. See, I don't know what my calculator did some wacky stuff, or my whole computer did wacky stuff. So we're gonna give that a minute. And let's talk about the next one, and then maybe my calculator will be up by then. Yes. I can show you mine as well. Yep, that looks good.
Oh, it's already first.
Huh?
Nothing.
Yeah. No, it was the right direction on my side. I could see it the right way. I think it just looks reversed to you. I don't know why. Okay, let's try it again. I can do this. This browser calculator is like one of the best things I've invested in. It's really not that expensive. I mean, maybe it would be for like everybody that's not me, but because I teach online and I share it with Apple TV with my students at the high school, it's worth it. Let's see what happens. It's thinking about it. Oh, it gave me an error. What the heck? Oh, yeah. Okay. One more time with feeling. If it doesn't work, then we're going to forget about it. Okay. And I also could show you how you can put the fancy math if you want I'll do it twice. The fancy math can go into this one as well. Only if you're brave, because it's a lot of parentheses and things. This one will work. Actually, this one will be a good example. So let's take a look at the last example, and I'm going to show you this one in the web browser if it shows up. There we go. This next one I'm going to show you in there. So let's take a look. So suppose that a random sample of 120 Americans who regularly listen to music using headphones results in 26 out of 120 having hearing trouble. What might you conclude? So I can sit here and calculate my p-hat. So 26 divided by 120. So take 26 divided by 120. My p-hat is approximately 0.217. So we're looking for the probability of getting 26 out of 120, 26 or more having hearing trouble. So take a look when I go into my browser or my normal CDF. This is the fun stuff. Okay, so we're looking for 26 or more So I'm going to put my math in here for my p hat. So 26 divided by 120. So my p hat, I just put it in as a fraction. Because why not, right? And my upper would be 1e99. The nice thing about this is it eliminates some of the math errors that we make. My mean is the same, 0.15. I'm going to type in the standard deviation, and then I'm going to come back in and do math with it instead. So the standard deviation we got was this right here. So it was 0.02. So it's about a 2% chance of getting 26 people with hearing trouble. I'm going to go in again and I'm going to put math in that second part, or in the standard deviation. Take a look at this. So I'm going to do parentheses 0.85 or 0.15. Doesn't matter the order really, but times 0.85. Close my parentheses. Divide by 120 because that's my sample size. Then close the parentheses. When you are putting the math in here, you need to be really careful with your parentheses. You need lots of them. Notice how I have parentheses around my entire numerator, and then I have parentheses around the whole thing. So I'm going to paste that. Here again, I still got I still have 2%. But instead I had the calculator do that math for me. Calculator's smarter than I am. So I'm going to go back here. And so that was normal CDF. And it was my p hat of 0.217 to 1e99. And then 0.15, comma, 0.03033. We have this right here yielded an answer of about 0.02. So notice that in this question, our random sample was of Americans who regularly listen to music using headphones. Because it would be an unusual to get a sample size of Americans, all Americans, not just headphones, that has 26 with hearing trouble, we can maybe draw a conclusion that the headphones could be causing hearing trouble. That's the kind of answer that you would be able to say here. And almost always when you get something that's unusual, you say more studies are needed, something like that. Questions. It's our last slide. So questions for while we are on being recorded. That was really poor grammar. I'm sorry. Questions for the whole class.
No.
Okay. All right, I'm going to turn off the recording.